I'm Doug Fern, and this is my take on music recording. I spent about half my career recording on magnetic tape, and for those of you who missed that era, I understand the attraction of tape machines. But I really do not want to go back to tape. Too many limitations and idiosyncrasies, too much maintenance. But in today's world of black boxes, tape machines are exotic. If you take the cover off of most any piece of recording gear these days, what you see is an incomprehensible collection of integrated circuits. Nothing you see tells you about its function. But look at a tape machine, and at least for the mechanical part, it's pretty easy to understand. It's like looking at a piano or a steam locomotive. The function is obvious, even if the details are obscure. But that's enough on the allure of the tape machine. This topic will be broken down into 3 separate episodes: the basics of magnetic tape recording, tape machine alignment and maintenance, and using tape in the studio. None of this is in any great depth, but just to give you a sense of how tape works. Let's start by delving into how magnetic tape and tape machines work, at least on a very simple level. Oh, and it's just a parenthetical note, in the world of pro audio during the tape era, a tape recorder was a home device. What you used in the studio was a tape machine. Same thing, just different context. So if you want to sound knowledgeable around older engineers, call it a tape machine. The first thing to understand is that magnetic recording is a good example of the intersection of electricity and magnetism. Other common things in our audio world also rely on this phenomenon in one way or another. Speakers, headphones, guitar pickups, dynamic and ribbon microphones, hard disk drives. In the tape machine, we rely on electromagnetism. Electricity and magnetism are closely related and pervade much of our technological world. If you take a piece of iron or steel, say a large nail, and wind many turns of insulated wire on it, and then connect the ends of the wires to a battery, the nail will become a magnet. But when you disconnect the battery, the magnetism disappears. This is useful in many everyday gadgets. For example, if you hear a tiny click from inside your electric oven when you turn it on, what you are hearing is a relay. A relay is an electromagnet that causes a hinged arm to move when it is attracted by the magnetism. This arm has contacts that complete a circuit and permit electricity to flow to the heating element in the oven. Why do that? Why not just use the switch you push? Well, most modern appliances use very inexpensive switches that could not safely carry the high power needed for an oven. A relay allows a small switch to control a much bigger switch. But back to the electromagnet we just made. If instead of the battery, we connect our electromagnet to the output of an audio amplifier, the magnetism generated will follow the amplitude and frequency of our music. Interesting, but not particularly useful unless we use that varying magnetic field to affect a material that can be permanently magnetized when exposed to the field. If we move our material across our electromagnet, the varying magnetic field will be transferred to the material. Congratulations, you have just made the world's crudest magnetic recorder. Okay, those are the principles. How do we make this practical? Well, the first magnetic recorders used a steel wire to receive and preserve the varying magnetic field. This was a concept invented in the late 1800s. It worked, but it sounded awful, worse than the lousiest 78 RPM records of the day. It took a lot of refinement to make a practical recorder. The first step was to dispense with the steel wire and replace it with a tape. The earliest magnetic tape used a paper strip coated with what was essentially rust, iron oxide. Later tape used acetate, an early plastic. Better plastics like polyester came later. Of course, it's not that simple, but the point is that iron oxide is a material that can be ground into a fine powder and coated onto the paper or plastic with some chemicals to bind it. The mechanical part of a tape machine is straightforward in theory, but challenging to do well. The magnetic tape unwinds from a reel, conventionally on the left side of the tape deck, and travels past guides, some of which can pivot, others rotate, until the tape arrives at the magnetic heads. We'll get to those in a minute. The tape passes in close contact with the heads and then past a precision shaft, the capstan, that along with a rubber roller control the speed of the tape. Then it goes past some more guides and then to another reel on the right. Sounds simple, but this mechanism has to have a high degree of precision to work well. The tape has to have an optimum amount of pressure against the tape heads. This is provided by some reverse tension on the supply reel, which is connected to a motor that actually runs in the opposite direction, trying to pull the tape back onto the reel. Needless to say, this tension is critical for proper tape-to-head contact. Even the slightest gap between the head and the tape will severely diminish the high-frequency response and reduce the level. In early tape machines, the motor back tension was constant, but the amount of tape on the reel was constantly changing, so the tension when the supply reel was full was considerably different than when it was almost empty. The last couple of generations of tape machines compensated for this and had a much more constant tension to ensure good head contact. The capstan determines the tape speed. 15 inches per second was fairly standard for most music recording, which provided about 30 minutes of recording with a standard 10-inch reel of tape. 30 inches per second improved the performance a bit, but it introduced some new problems. And it used up tape twice as fast, so you only had 15 minutes on a reel. 7.5 inches per second was an option on many machines, but performance at this speed is not very good. The faster the tape moves past the head, the more detail can be resolved, at least in theory. 15 inches per second was an ideal compromise. The capstan is a metal shaft about 1/4 inch in diameter on most tape machines. It must rotate at a constant speed to meter the amount of tape passing by. Up until the last generation of tape machines, the capstan was the shaft of a synchronous motor. A synchronous motor is designed to rotate at a speed locked to the power line frequency, 60 Hz in the Americas and 50 Hz in most of the rest of the world. We tend to think of the power coming out of the wall socket as pretty nasty stuff that needs a bit of work to make it suitable for high-performance audio, a task that is taken care of by careful power supply design in professional equipment. The notion of nasty power is correct for a lot of reasons that aren't relevant to this discussion, but one thing that is remarkably accurate is the frequency. It has to be that way so that multiple power plants can be connected together to form the electrical grid. Therefore, the frequency is maintained with great precision. For example, if you have an old-fashioned analog clock that plugs into a wall socket, chances are that that clock relies on the 50 or 60 Hertz power to keep it accurate, and that works surprisingly well. So it is with a synchronous capstan motor. But the rotation speed of the capstan is not the only thing that regulates the tape speed. There is always a small amount of slippage between the tape and the capstan, and this can depend on the cleanliness of the capstan and the pressure roller, the amount of pressure the roller exerts to sandwich the tape between the capstan and the roller, and the cleanliness of the heads and guides, the amount of tension from the supply and take-up reels, and even the tape formulation. With all those variables, it seems amazing that the speed could be all that accurate. And it's not. The speed of most legacy tape machines changes slightly, especially from the beginning to the end of the reel, as the tensions change. The last couple generations of tape machines were a lot more sophisticated, with crystal-controlled capstan motors and reel motors that adjusted their tension so that it was constant throughout the reel. Still, an oxide buildup from the tape could increase the friction enough to affect the speed. These variables show you why it is not possible to fly in a track from another tape machine with any kind of accuracy. Sure, people did this and made it work, but imagine the tedium of keeping an added track in sync. Digital, of course, makes that a non-issue. Okay, we have our tape transport working reasonably well, and we are ready to try recording something, but we're not there yet. Early experiments in magnetic recording revealed a ton of problems to overcome. The biggest one is the nonlinear nature of magnetic tape. Okay, so what do we mean by nonlinear? Let's first look at how a linear system should behave. We'll take a precision source of a pure sine wave tone to make this easy, and a precision meter of some sort to read the level. If we connect our source, a signal generator or oscillator, to our meter, assuming both are perfect test instruments, as we vary the amplitude or loudness of our audio sine wave, the meter should show that for every 1 dB we change the output of the oscillator, the meter will change by precisely the same amount. This is hard to mess up with just a wire connecting the two. But instead, let's put a device like a vacuum tube or a transistor in the path, configured as a simple amplifier. Now, when we vary the amplitude of the oscillator, chances are that the meter will not show an exact 1-to-1 ratio. In other words, if we increase the level by 1 dB, the output of our little amplifier might only increase by half a dB. Or we might increase the level by 1 dB and the output goes up by 3 dB. Obviously not an accurate representation of the test signal. Replace our tone with music and it's not going to sound right. Perhaps the low-level audio will be much too quiet and the high-level sound will not be as loud as it should be. Properly implemented, we have created an expander and a compressor, useful tools in some circumstances, but not an accurate representation of the original music. The amplifier is non-linear. Unfortunately, this is a characteristic of all amplifying devices, vacuum tube or solid state. And it's not just a level problem. Various other types of distortion will also occur. Wow, big problem. But clever researchers figured out a way to mitigate this back in the vacuum tube era when they analyzed the curve of the input versus output, and when graphed, they could see that there was a section of the curve that was reasonably straight. The output went up the same amount as the input. The challenge was to shift our audio signal into that linear region of the curve. And this was solved by superimposing a small amount of constant DC voltage, which moved our audio into a more linear range of the curve. They called it bias because it provided a constant offset from the natural performance. Works great and forms the basis for all analog amplification to this day. Those integrated circuits in all your rack boxes are just a collection of lots and lots of transistors, with more transistors supporting them and shifting the bias to achieve linearity. Okay, back to tape. It's highly nonlinear, but we can't apply DC bias to our magnetic recording head to shift the range. DC would simply magnetize the head and seriously degrade its performance. So clever scientists came up with the idea of using an audio signal to lift the music into the more linear range of the tape, using a steady tone. But wait, who wants to hear an audible tone in the background of their music? That won't work, But what if you used a tone above our hearing range? Tape bias frequency is in the range of 50 to 100 kilohertz. Problem solved, but not without introducing its own set of new problems. And by the way, if you haven't figured it out already, we call that ultrasonic signal tape bias. We'll get to the problems with bias in a minute, but first we have to solve another problem. Tape is intrinsically very noisy, too noisy to use, and the perceived noise increases with frequency. I say perceived because our hearing does not have equal response to all frequencies. Our hearing is most sensitive in a range from about 1 kilohertz to 6 kilohertz or so, depending on the individual and how much damage you've done to your ears. This problem is not unique to tape. Phonograph records have the same problem, as does analog FM broadcasting. And all three of these audio systems use the same solution, pre-emphasis. This is a very simple but effective way to reduce the perceived noise level of a record or a tape recording. You boost the high frequencies when you record, and then roll off the highs when you play it back. The circuit to do this is stone simple, which was necessary for a mass-market medium like the phonodisc. The pre-emphasis used on tape, vinyl, and analog FM is all very similar. The boost starts quite low, around 1 kilohertz, and gradually becomes more intense until it peaks at about plus 15 dB at 15 kilohertz. Pretty extreme, but simple, and it works well and is easy to implement. We can get away with this major boost in highs because most music and voices has comparatively little energy in that top octave of our hearing range. So the tape is not overloaded. But some sounds, particularly percussion sounds, have overtones that go well into the supersonic range. And if these are missing, the percussion lacks impact and sounds mushy. Well, we are restoring them to their proper level, right? Yeah, but the damage has already been done because the high boost is likely to have exceeded the dynamic range of the tape or the disc. The playback is no longer linear. Fortunately, you can tolerate a lot of this and it does not sound bad, at least until you compare it to the pure version of the sound. In fact, the non-linearity of tape in general is a major part of its sound, for better or worse. Engineers in the tape era could use this as an effect to change the character of the sound. This probably explains most of the love of the tape sound. But there's yet another problem. When you have a lot of high-frequency content in the music or sound, those frequencies can interact with the ultrasonic bias and create new sounds that are the sum and difference between the original sound frequency and the frequency of the bias. The sum and difference sounds can end up in the audible range, and these new frequencies are not harmonically related to the music. In fact, they sound awful. So how do you prevent that? By reducing the level so that the pre-emphasis is no longer causing the tape to be saturated, and the unwanted frequencies are reduced in level by a corresponding amount. That's why on tape you can't record a piano at full level. Doesn't sound good at all. The high-frequency overtones from the hammers hitting the strings will generate a lot of those discordant, nasty-sounding frequencies. The same applies to other high-frequency sounds like cymbals or even a sibilant voice. Maybe you like that sound for certain things. It can be used as a tool. But for a piano to sound closer to reality, you have to record a piano at a reduced level, typically 10 to 20 dB lower than the zero reading on the VU meter. And of course, the noise increases by the same amount. Digital does not have this problem, although digital certainly has its own set of deficiencies. And this saturation, what is that? When the signal becomes too much for the tape to handle in a linear fashion, the output stops increasing in step with the input. The tape is said to be saturated. It just can't take any more. It's the same phenomenon as compression or limiting. Those can be useful, and so can tape saturation, if that's the effect you are looking for. Not only is the output not the same in dynamics, but with tape, the harmonic distortion goes up as well, sometimes a lot. The playback will not sound like the original sound. Fortunately, with tape, the resulting distortion tends to be musical in nature and can add fullness to the sound. Another problem inherent in tape recording is periodic variations in speed, which subtly change the pitch of the music. When this happens slowly, over a second or more, it's called wow. Faster speed variations are called flutter. Either can be very annoying to listen to. All recordings on tape have wow and flutter. The only difference is in degree. The pitch will slowly or rapidly vary. A little of this is not too noticeable, but a lot of it makes the music sound bad, since there is no stable pitch for our ears to grab onto. Plus, it makes it difficult to tune instruments for an overdub. These variations are caused by many things, but most commonly by wear in any of the mechanical parts of the tape machine. Still enthusiastic about recording to tape? Well, there's even more bad news. The tape machine is an electromechanical device, and there are many variables that have to be accounted for beyond the intrinsic problems with tape. If you only record and play back your tape on your own machine, some of this won't be a problem. But if you're sending your finished tape to a mastering facility, will their playback match what you heard in the studio on your machine? Probably not, and the results are not pretty if either machine is not properly aligned. A typical tape machine has about 5 adjustments for each channel, plus some overall adjustments. And we will get into the alignment process in the next installment on this topic. This is my take on music recording. I'm Doug Fern. See you next time.